So this is actually, I think, week 6 of Introduction to Abstract Group Theory course. So what we have done in this week is basically we have did what is the even and odd permutations. And alternating groups. And group actions. So these are the three main topics that was covered in this week. So let's go one by one. So before going that, okay, first what we'll do is we will try this. We'll do a little bit about this even and odd permutation. Okay, so if you look at the lecture, there is one way of defining even and odd permutation, right? So what you do is you take any sigma here, which belongs to Sn. So one of the theorem says if you take any sigma, you can write it in as a product of transpositions. Okay, where this k is a where this tau is a transposition. So transposition is basically an element of this type. It only permutes two elements and fix everything else. Okay, so those are called transpositions. Probably have to write it properly. So what we have done is, if you have any permutation, you can write it in terms of transposition. So what we also observed is this is not unique. Okay, so this product is not unique. There is many ways you can write it. So in that sense, there's no uniqueness here. But what is unique is this, and also this number k. This is also not unique. Okay, so there can be many k here. It can come. So element can be transposition. You can have two transposition. You can also have four transposition, which also represent the same element. But what we have observed is the parity of this is unique. So what we have seen is whether this k is odd or even. This is unique. So by unique, what I mean is if you give a permutation, whether this number when you write this sigma as a product of transposition, whether you can write it as you count how many transposition is there, whether that is even or odd is unique to the sigma. Okay, and we call that as a we say a sigma is even permutation if when you write it as a product, this k has to be even. Okay, and if the k is odd, it is called odd permutation. So that is what we did. So right now I will just do the same thing, but in a different language. Okay, so what we did is we write it down in terms of permutations, and then we did something, and then in order to say this thing is unique, we consider some the polynomials, right? Xi minus xj, this kind of polynomials you consider and you try to do it. But here I will give a little bit different argument to define the even and odd permutations. Okay, so maybe I will not go into full details, but what I do is I will just try to give an idea of what is happening. Okay, so what you can do, so let's start with the element sigma belongs to this symmetry group. Okay. So let's consider these elements, this kind of a vector. So let me call 1, 0, 0. This is a n vector. I mean, the size is n, but the first one is 1, the rest everything is 0. Okay, and I call this vector as a e1. And similarly, I can define e2, where the second coordinate is 1 and the rest of the coordinates are 0. Okay, so one can in general define what is ei, which is everything is 0, but 1 in the ith coordinate and the rest everything is 0. Okay. So now what you can do is the following. So if you take this E1, E2, E3, En, okay, this Sn will act on this. Anyway, later we will do the group actions, but this Sn will act on this. Or in other words, I can again say something like this. So I will skip the group action here. I will directly go what is happening. So from Sn, there is a homomorphism into the matrix space, or I will write the general linear space, GLN, let's say R. Okay. So how you do is you take this sigma and then you map it into the matrix of this form. Okay. So what you do is here you do E of sigma of 1, E of sigma of 2, E of sigma of n. Okay. Okay, I will I will explain it a little bit what is actually happening. So basically, let's say my sigma is 1, 2, 3. Okay. Then what is E of uh, sigma of 1? This is nothing but E of 2. Okay. So if you take this particular permutation, so what is the matrix corresponds to this is basically you can just write these things down and you will get 0, 1, 0, 0, 0, 1, 1, 0, 0. You can compute here. E of sigma of 2 is what? What is the sigma of 2? Sigma of 2 maps to 3, right? So sigma of 2 is E3. So that's what I'm writing, E3 here. And you can write what is sigma of 3. Okay. So this is the matrix that corresponds to this. Okay. So here I have matrix of this type. So one thing you can observe is one can actually prove it, which I'm not going to do. One can actually prove that this matrix is actually invertible. Okay. This we can do it. Okay. So in that sense, and also what you can prove is this map is also injective. So let me call this as some F. Maybe I'll erase this part. So far what we do is you take Sn and then give map to GLN. Okay. How you do? You take any sigma and then map it into matrix of this form. Okay. And this matrix is called permutation matrix. It's called a permutation matrix associated to sigma. Okay. So what you can prove is probably you keep it as an exercise. Let me call this map F. You can prove that F of sigma belongs to GLN of R. So in fact, R here is not really important. You can put any field here, so that doesn't matter. So okay, maybe I will solve it here also. How do you say that F sigma belongs to GLN? GLN is what? It's a set of all matrices which are invertible, right? So what you can prove? So here is the hint. I will give the hint also. So if of sigma belongs to GLN means what I have to do? I have to give you the inverse, right? So note that observe f of sigma inverse is nothing but f of sigma inverse. Okay. And also you have to observe that this is a homomorphism also. Okay. So you can prove that sigma is a homomorphism. So not sigma, f is a homomorphism. Okay. So, and the another thing that you prove is F is injection. Okay. So, what are the things you want to prove is you have a homomorphism, and this is an injective homomorphism is what you want to prove. It's not hard to prove. You can try and see. You just find what is the kernel. Okay. So, if you want to find what is injective, I will here also I give you the hint. These are very easy to find it, but I will just leave it for you. The reason I'm leaving it is kind of this is not the part of the course that was done. So I just want to give a different view, because this is the view, this is the way that I kind of like it, and it's more when you do that you can actually understand what is happening. So when you go via the polynomials and all, it's hard to see what is actually happening, but this way kind of gives you the idea of what is happening. So what you do is you find the kernel here. It's easy to find. And find the kernel and say it is actually the identity. The sigma is identity is the only element. Okay. So far what we got is this F is a injective homomorphism. So what you can see is this Sn is kind of a subgroup of this GLN. Okay. From this GLN there is a map, right? This map is called determinant map, and this basically goes to R star. Okay. But what you can prove is this permutation matrix. You can prove that it goes to plus or minus 1. Okay, so this you can prove it. Okay. So prove this also. Prove that f of sigma, so determinant of f of sigma is belongs to plus or minus 1. Okay. So how do you prove this? Here also I will tell you the idea. I'm not really proving it, but I will kind of tell you the idea. See, if you swap, if you know about the determinant, what you know is if you swap two columns, then the determinant change by minus 1, right? So whenever you swap two columns, the determinant change by minus 1. Okay. So here what you're doing is you are swapping is the multiple times. Okay, so that is what is happening. So sigma 1, so whatever, when you have something like this, it just tells you are swapping it multiple times. Okay. So you have this determinant map, and it goes to plus or minus 1. Okay. Now if you take the sigma and then go all the way here, okay, so the image is either plus 1 or minus 1. It's 1 or minus 1, and this is called the sign of the permutation. Okay, so this is also one way you can do the sign of the permutation. You go take this Sn and put it inside GLN and take the determinant map. Okay, so whatever the image of this is either plus 1 or minus 1, and that is called the sign of the permutation. Okay, and you can actually also prove that whatever we do here and whatever we did in the class, these are all same. Okay, so either way you go, the sign remains the same, because one can also ask a question. See, in class we have some polynomial using some transposition, and here we are going via the determinant. Whether the sign will remain the same or will be different, one can also prove that this sign, whatever you get via this map, so you take the sigma wherever you go, that is the sign of the sigma. And one can also prove that this sign and that one we defined in the class are all the same. Okay, anyway, so, but I'm not going to define much here. Okay, probably here I will just mention why in this part, if you take here, why this is plus or minus 1. That question I said, right? So I said this is actually plus or minus 1. So let me tell you why it is plus or minus 1. But with some example. So what happens with this permutation matrix is this kind of permutes that columns of the identity, right? So if you write something like E1, E2, E3, this is nothing but identity matrix. Okay, this is 1 0 0 0 1 0. Okay, so this is just identity matrix. So now what happens here is, here you are just kind of permuting the column of the identity matrix, right? So maybe yours will be something like this. Sorry, this is maybe one permutation matrix. But when you want to compute the determinant, what you observe is every row and every column, there is only one here. So you try to use this Lagrange multiplier or whatever the way you want to do. Let's say you expand in this way. Okay, so you kill both of this. So what you get the determinant as 1 times this you kill. So this is 1 again. Okay. Suppose if I have a different matrix, let's say something like this. Now if you, let's say you take the determinant again. So what you get? You start with this expand via this row, right? So that is minus 1 times. So this is 1 again. Okay, so if you want to prove, you always kind of prove via the induction. So go via the induction. In order to prove this determinant belongs to plus or minus 1, use induction. Okay. So I will give a hint also again here. Because for 2 cross 2 matrix, it's easy to see, right? So if you have a 2 cross 2 matrix, let's say the only possible permutations are only this, either this one or the other one. Okay. Here, if you observe, the determinant is plus 1. Here, the determinant is minus 1. Okay. Determinant is plus 1. And now, if you have a 3 cross 3 matrix, let's say, however the 3 cross 3 matrix is, you expand via one row. Okay. So what you can see is this row has only one, and the rest of the things are 0, because we are kind of permuting the, or probably you expand via this column. Okay, expand via this column. So what you can see, since we are permuting the columns, permuting EIs, the EIs has only one is 1, and the rest of the things are 0, right? So that one you take, that comes with a plus 1 or minus 1. We don't know how it comes with, but it comes. So because here you are expanding, and the first term is actually plus. You have this checkerboard thing, right? Plus minus plus plus minus, something like this. If suppose the 1 is here, then you write plus 1. If the 1 is here, then you write minus 1. Okay. Then what happens is, once you do that, you will erase this row and column, and what remains is n minus 1 cross n minus 1 matrix. There you use the induction step, and then you compute it. Okay. So use the Lagrange expansion and use induction and Lagrange expansion. So basically the expansion formula. Okay, so you can easily prove it. But anyway, my aim is not to actually spend so much time into this, but I just want to say there's a different way you can see the sign of the permutation, and in some sense this is more easy to remember. All these formulas are hard, like the polynomials are you don't know what is happening, but here you can see we are seeing Sn as a subgroup of GLN, which is given by the permutation matrix. Take the determinant, what you get is the sign of the permutation. Okay, this both sign will remain the same. Okay, so let's have this way. So this, if you want to prove that, these are the exercises you prove, and some of these things I gave you the hint. So whenever it is hard, I kind of gives you the hint. Okay, so it's not hard. At least this I kind of told you what to do, but I haven't actually spent time proving it, because there are other problems we do, and this just I want to say. Okay, so let's move on to a different question here. I will delete this page. Okay, so let's move on to question 1. So this question says you the following: if sigma square is an even permutation, so what you have to do is prove that sigma square is an even permutation. So let's prove it. So what we know is the following. So I will do it with the two method, and so you can see how this methods are used. Okay. So the method one. So what we have seen is this an is nothing but even permutation, right? This is a set of all even permutation. Okay. And what we have observed is Sn by an. That's a map from here to plus or minus 1. So I will write 1 comma minus 1 rather than plus or minus 1. Okay. This map we have. What you do is basically all the odd permutation goes to all the even permutation goes to 1, and all the odd permutation goes to minus 1. Okay. So this map we have. Okay. So once you have this map, what you observe is whatever the sigma is here, if you take the sigma square, it will go to 1, right? 1 here. Or maybe I'll just write this here. Okay. So I'll probably will do something like this. Just give me a minute. I will write something else. So you take Sn and you go to Sn by An. Okay. So what does it means by even permutation? Even permutation means, so what we want to prove is we want to prove that sigma square belongs to An. So this is what we want to prove. So we start with the sigma belongs to Sn. We want to prove that the sigma square belongs to An. Okay. But if you look at the size of this one, okay, the size of this is basically 2, right? This is 2. So what you do is you take sigma. Let me call this as a pi. So pi of let's say sigma square I apply. This is a pi of sigma the whole square. Okay. But this is equal to 1. So in this group, this pi of sigma square you take here, and then you apply the pi. In this group, it became 1. Okay. So what does it means? It means that the sigma square belongs to An. That's all. Okay. So that means sigma square is an even permutation. Okay. So there is another way you can write it. Another way is you take sigma and write it in terms of product of permutation. Okay. A1. Okay. I will write. Okay. How do you write? Let me write A11, A12, etc. AR1, AR2. Okay. Now, if you write a sigma square, the sigma square will basically become A11, A12, this etc. AR1, R2 times. Again, you do the same thing. Okay. So, how many permutations are here? There are actually whatever the number here. I don't know what it is. Let me call this as R is there, and this is also R. So there are 2 R permutations as well. So sigma square can be written as product of 2 R permutation, but 2 R is 2 R is so how many terms here? If you look here, there are 2 R terms here. So this is even. Okay. So that means sigma square is a even permutation. Okay, so this is the easy way. You can also go via this kind of maps. But I will just, since we have done this, I will go via this one also. Okay. So just recall this. We have Sn to GLN, and then you take the determinant and you go to R star. But the image is basically plus or minus 1, right? So this R star is a map under multiplication. So you take the sigma here, and when you go here, you will get either plus 1 or minus 1, right? So basically, this is the sign of sigma. The composition is called the sign of sigma. So if you go to sigma square, so what you observe here is whichever the element you take here, okay, and then here you go. So what you observe is this is kind of like a homomorphism. So this became a sign of this map is a homomorphism, right? So let me call this map as some F or something. The composition I called it as F. So this is F of sigma square. Okay, but in this group, plus or minus 1, if you square any element, you will get 1, right? So if you get 1 means the sign is actually the sign of sigma square is equal to 1. So that means sigma square is a even permutation. Okay, so this much we have. So let's move on to the next question. So the next question says that the sign of permutation, it obeys the following law. So what happens is if you have a permutation which is even, and if you have another permutation, let's say sigma 1, sigma 2, this is even, then when you multiply these two permutation, what you get is a even permutation. Okay. And similarly, if you have odd permutation and odd permutation, if you multiply it, you will get even permutation. Okay. So if you have a different parity, even and odd or odd and even, then you will get odd permutation. Okay. So the proof is actually easy. So there are anyway here also there are many ways you can do it. For example, you can go via this maps and you can do it, or you can just write it down like this and you can do it. Okay. So here at least I give you 3 methods, and similarly here also you can do multiple ways, but we will just do the easy ones. Let's say you take two permutation. Let's say sigma and tau. Maybe not tau. I will just write sigma 1, sigma 2. Let's say this belongs to Sn. Okay. And let's prove the first one. Let's prove this part. Or maybe we'll do something general and then we'll do it. Let me write sigma as a product of, let's say, AI1, AI2. Okay. I equal to 1 to, let's say, n. So not n, maybe r. And let me write a sigma 2 as again the product equal to 1 to, let's say, s. Okay. So now if you write sigma 1, sigma 2, this will be this product, right? This product varies from I equal to 1 to r, AI1, AI2. And again the product I runs from 1 to s, AI1, AI2. Okay. So if this sigma 1 can be written as a, let's say, as a product of R permutation, and sigma 2 can be written as a product of S permutation, then sigma 1, sigma 2 can be written as a product of R plus S permutation. Okay. So now you observe, if you add two even number, you will get a even number. So the sign of the sigma is basically the parity of this, right? Whether, what is the sign of the sigma? Whether the R is even or odd. Okay. So if R is even, then the sign of the sigma is even. If r is odd, then the sign of the sigma is odd, right? So what happens is when you multiply it, the number of, you can write it in terms of r plus s transposition. So what we have is sigma 1, sigma 2 can be written as r plus s transposition. Okay. So from here you can directly do it, right? So if you take two even number, so if you take two even permutation, that means these two numbers are even. And what is the r plus s? R plus is also even. If you take two odd numbers, then these two are odd. What is r plus s again? Sum of two odd permutation is odd permutation. So sum of two odd permutation is even permutation. But if you have an even number and odd number, and if you add it, you will get odd number. And similarly here, if you have an odd number and even number, you add it, you will get odd number. Okay. So that's all. You just have to observe that this can be written as r plus s permutation. Then you directly, say that this rules holds. If you have even and odd numbers, this rules holds, right? So basically, even plus even is even, right? So you have to use that particular property because r, if both of them are even, then the addition is even. That's it. Okay. So there is this kind of laws are kind of holds. If you go in this particular way also, you can again prove it. So if you take 2 sigma 1 and sigma 2, what happens is here what you get is you get the sign of sigma 1 times uh, sign of sigma 2. Okay. So if you take sorry, just give me a minute. Yeah, sine of sigma 1 times sine of sigma 2. But in this case, what happens is this is plus 1 or minus 1. Okay. So the plus 1 means even permutation, minus 1 means odd permutation. So basically, this is not actually sine. So I have to write, let me just call this as f, okay? Rather than, okay, I will probably write it here. So what you get is you get a map to plus or minus 1. Okay. So 1 means even permutation, minus 1 means odd permutation. Okay. So if you take sigma 1 and sigma 2, then where it goes? It goes to f of sigma 1, f of sigma 2. Okay. So here you observe, if you take two numbers, like if you take 1 and 1 and you multiply. So if this is what even and even, right? So you take 1 and 1, multiply, you will get 1. Okay. Odd and odd means what? You take minus 1 and minus 1, multiply, you will get minus 1. Okay. So if this is odd permutation, means f of sigma 1 is minus 1. Okay. If both of them are odd, that means minus 1, minus 1, this is 1. And similarly, you can do for other ones. Okay. So whichever the way you do, whether you want to use this way or you want to use this one, it kind of remains the same. Okay. So there is no difference here. And of course, one can prove that this, whatever the sign you get is same as the whatever the sign we did in the class. And that part I'm not going to prove it, but one can prove it. Okay, since we have done so many, the problems in permutations last week. So, sorry, not last week, last lecture, that the Monday there's another tutorial, right? That we have done so many problems. So we will do. So I plan to focus more on the group action rather than the even and R permutation. I just want to say there's another way, and let's focus on group action. So the group action of a group G on a set A is basically the map G cross A to A. Okay, so basically it is a map from G cross A to A. Okay, so you take a G comma A, you map it into G dot A. Okay. So G dot A is again an element of A, and it has to satisfy the properties. If you multiply, if you take one action and then you do another action, it's same as you multiply these two things and then take the action. and identity kind of have to act trivially. Okay, so 1 times A has to be A. If anything that satisfies these two properties, any map from G class A to A satisfies these two properties, we say that this group G acts on A. Okay. So let's prove this thing. So what we have is you have the additive group B set, and it's gonna act on itself by this particular action, and we want to say that this is a group action. Okay. But let's first observe what is actually it is telling. So this Z act on A, how it acts, it is adding this Z here, right? So this Z acting on A, it basically add the Z. Okay, now what is actually happening with this Z? So let me draw it here, and you can see what is actually what I mean by action here. So let me take this as maybe 0. 1, 2. So let me take Z as 1, let's say. Now if I act on the integer, so what happens here? So what happens is this 0 will go to here, 1, right? And the 1 will goes to 2, and the 2 will goes to 3. So these things kind of moves around. So that is what we are doing here. So basically here's the elements here, and when the group acts on these elements kind of, there is something happening in the elements, and that is what we call this action. In this case, its action is translation. So okay, so when you do this, let's say if the Z is 100, then you are moving 100 steps, or maybe Z is 2, then you are moving 2 steps. Okay, so this action is translation. In different places there are different actions, but anyway. So basically group actions comes from this kind of geometric idea. A group can kind of act on a set here. Okay, so in this case, this group, you can see it as a action, I mean acting on this set by just moving it around. Okay, so let's prove it. So what are the things we need to prove? First thing is we need to prove that 1 times uh, identity is 1 times A is A, and we have to prove this kind of associativity. Not associativity, but similar to associativity. Okay, in this case, what is the identity? Identity is 0. So what we do is 0 times A. What is this? This is nothing but 0 plus A. But 0 plus A is nothing but A, right? So what we got is 0 times A is A. By the way, this is not multiplication. This is an action of 0 on A. Okay, so the action is, it's moving. So the second property is done. Let's do the first one. So what is first one? First one is Z1. See here you can see G1, G2 acting on A. So let me write. You can just see it one more time. Z1 acting on Z2 acting on A. We want to prove that this is equal to Z1, Z2 acting on A. Okay, so this is the claim. So let's try to prove it. What is this? Let's do this one. So this is Z1 acting on Z2 plus A. But this is nothing but Z1 plus Z2 plus A. So this I can write it as Z1 plus Z2 acting on A. Okay, so in this, when I write like this, it is basically the operation here. So here the operation is kind of suppressed, but when I write G1, G2, it is the G1, G2 basically group as some operation, right? So when I write, it's a composition in that one. So in this case, what happens is you have to write a plus here, because the operation is addition. Okay. So this is what we got, and we got the first one. Okay. So similarly, we can do the second one also. I'm not sure if we want to do it, but we can do the second one also. So let me just copy it here. Okay, so let's do the second one. Here we have a additive group R. So, and this additive group act on the XY plane. Okay. So in this one Z acts on itself, but here now R acts on R2. Okay, how R acts on R2? So you take R times XY, and this is nothing but X plus RY, comma Y. So let's prove the both property. So the first property says if R equal to, this is the additive group again. So the identity is 0. So what we have to prove is 0 times XY is nothing but XY. Okay, so this is the second property, which is kind of the identity acts trivially. Okay. So let's write it. What is 0 times XY? This is nothing but X plus 0Y. Okay, here you observe when he writes ry, this is the multiplication in the real number. Okay, so 0y is basically 0, so this is xy. So the first one is done. Let's do the second one. So the second one, what you want to do is r1 times r2 times xy. Okay, and you want to prove this is r1 plus r2 times xy. So the operation is addition here again. So here you can see it's additive group. So let's do it here. R1 times. So let's see what is this one. This is nothing but. So here, recall this is the definition. So this is a x plus R2y. Okay. Comma y. And this is x plus R2y. So this is again, this is a x term now. Okay, this became my x term, and this is kind of the y term. Okay, so that's plus R1y. But this, if you write, you can write it as x plus R2. So we use the properties of real numbers, every property of real number. So here we get R2 plus R1 times y, comma y. But this is same as R1, R2. So this kind of commutes. It's a abelian group, right? So it's commutes. So this is nothing but x. Sorry, this is basically what? This is basically R1 plus R2 times xy. Okay. So just apply the definition, you will get this. Okay. So basically, this R acts on Ry like this. So maybe you can try to see what exactly happening with this action. So here we did geometrically, right? Maybe if you're interested, you can try to see how this action looks like. So, I mean, I didn't actually try to see it, but probably one can actually try to see. Anyway, I didn't actually try it. So, but if you're interested, you can try to see how geometrically this works. Okay. So let's move on to the different question. So another thing is whatever we are going to do, it may be later whatever that comes, it may be a little bit harder than whatever we did the yesterday tutorial, because the yesterday we plan to do the easy ones, and today we try to kind of improve the little bit the hardness. So yeah, so that's just I want to say, that's all. Okay. So here what we do is let's H be a group and it acts on this set A. Okay. Now we are going to define a relation on the set A. What we do is if A is related to B, if and only if A equal to HB for some H. Okay, so let's take some minutes to understand what is happening. So what we want to prove is we are defining a relation on A. Okay, so here we have A and we are defining a relation on A. What you do is you take two elements of A and you say A is related to B. What you do is you find only A equal to H times B for some H belongs to H. So if there is a H which takes this A, this B to A, and then we say this A and B are related. Okay. So in this case, if you go here, so here this is the relation, right? This Z acts on itself. Okay. So whether these two elements are related, if you want to say, yeah, these two are related. Because why? Because this one takes 0 to 1. Okay, 1 times 0 is nothing but 0 plus, sorry, 1 plus 0. So 1 times 0 is nothing but 1 plus 0, which is 1. So this 1 takes this 0 to 1. So these two are related. Why? Because 0 is nothing but, sorry, 1 is nothing but 1 times 0. Okay, so this 1 and 0 are related. Sorry, 0 and 1 are related. Now, what the question is? The question is this relation that whatever we defined here, we want to prove that this is a equivalence relation. Okay. So you know what is a equivalence relation, right? So when we did the coset, we might have done what is a equivalence relation. So I'll just write what is a equivalence relation, or maybe I'll just recall what is a relation. Okay. So a relation. Okay. Maybe I'm not sure if I want to recall the relation. Basically, okay, maybe I'll skip the relation. So relation is basically a subset of a Cartesian product. So let's say we have A cross B. A relation is basically some subset here, some subset K of a Cartesian product. This okay. So basically, if A, or maybe I will write R here. Relation is basically a subset. We say that A is related to B if this AB belongs to R. Okay. So basically, relation is just a Cartesian product. Maybe one can see, so there are examples one can give, but let's not go into those things. Let's assume that you know the relation, and I will try to do after that. So a relation is called equivalence relation. So if the following properties are satisfied. Okay. So what is the first property? First property is A is related to A. Second property is A is related to B, implies B is related to A. And the third property is if A is related to B, and so here this means and B is related to C, this must implies that A is related to C. Okay. So this property is usually called as a reflexive. Reflexive, I don't know what they call reflexive, but you can see this kind of reflecting. It's the same elements. So A is again related to A. And this one is called symmetric. Okay. And this last property is called transitivity. And if any relation satisfies these three properties, it is called equivalence relation. So you already know it, but I just recall it. So what we want to prove is we want to prove if H acts on A, and we give a relation A is related to B if A equal to HB for some H. We want to prove that this relation is an equivalence relation. Okay. Maybe I'll copy the thing again in the next slide also. so that you can remember it. So you can remember what is the relation here. So let's try to prove that this is equivalence relation. In order to do it is a equivalence relation, you want to prove the three properties. So let's start the properties one by one. So first property, let's do the reflexive. Okay. So what we want to prove is we want to prove A is related to A, right? So what we have to say, we want to find some H such that A equal to HB. We want to write like this. So what is the H you can do? You take the H as identity. Okay. Then A is related to 1 times A. Okay. So that means, no, sorry, A is equal to 1 times A. Because we know that 1 times A is A, right? That is one of the property of a group action. See, in fact, the group action, this property is defined in such a way that this relation became an equivalence relation. So if you have done the Lagrange theorem and you might did all this coset or equivalence classes, etc., right? There you can see why the equivalence relation is important. So equivalence relation has some property. For example, if you have equivalence relation, it kind of partitions the set. Okay. So those kind of properties are important, and hence if you have a equivalence relation, it will be good. So this condition in the group action is imposed in such a way that this relation became an equivalence relation. But anyway, so let's do the second one. Second one is symmetry. So what we do is we assume that A is related to B. Okay. Let suppose A is related to B. What we claim is B is related to A. So what is A is related to B means? This is the same as telling that A equal to HB for some H. Okay. So equal to H times B. Okay, from here, how do you say B is related to A? Okay, so what you do is here you have A is equal to H times B. You take this, and in both sides you multiply with H inverse. Not multiply, but you act by H inverse. Okay. Now you have a property of action, right? So this is nothing but H inverse. H inverse H acting on B. But that is nothing but identity acting on B, and that is B. Okay. So there we got here. So see this kind of, for example, here if you go with the group action, where's the definition of group action? See, one can also say, see, any map from G cross A to A. So basically, what does it tells you? It takes you take a this element G will hit this A to some other element. Okay, it can hit to this element or whatever. So it basically this Z take one element and it kind of hit it to other element. Okay, so one can say, okay, this is a group action, but the point is this is not enough for us to say anything more than like whatever we want. This is like very weak condition. So these two properties are imposed in such a way that there is a good theory later. So if these two properties are imposed, see here you can observe here. This is also we need it here. Okay. So these are imposed in such a way that this relation became equivalence relation, and then we can talk about the equivalence classes, etc. So later it will be important. So this kind of condition are imposed in the group action so that the theory is kind of useful. Otherwise, it's not useful. That's why those conditions are needed there. Okay. So we have proved the symmetry. Let's prove the transitivity. So okay, A is related to B and B is related to C. We need to prove that A is related to C, right? So let's write down what does A is related to B and B is related to C means. So A is related to B. This implies A equal to HB. So B is related to C. This implies B equal to, let's say, some GC. Okay. Now we want to say that A is related to C. Okay. So let's probably I'll put a dot here. Okay, so A equal to H dot B, but B is equal to G dot C. So this is a H dot G dot C. Okay. But I can use the property. This is H G dot C. So what happens is A is equal to H D G dot C. C it has a one element H, let's say. So A equal to something dot C. So that means A and C are related. Thus, is related to C. Okay. So we have proved that this relation, whatever we have, is a equivalence relation. Okay. So we have proved this relation is a equivalence relation. Okay. Once you have an equivalence relation, what happens is you have a partition, right? So let's say each X belongs to A. The equivalence classes of, okay, this probably I will explain a little bit and maybe we will do here. So once you have this equivalence relation, what this equivalence relation do is it kind of partition the set. So you have your set here, let's say A, and you take this A and look for all the, define the equivalence class. This is set of all B belongs to A, such that B is related to A. Okay. Take all the elements that are related to A, and you can see that kind of partition your set. Okay. So by partition, what I mean is, if you take two elements, A and B, then this equivalence class is either the same. Sorry, equivalence class is either the same, or the equivalence class intersection is empty. Okay. So it kind of breaks this things like this, and this is what exactly we did in the Lagrange theorem also. So the coset kind of breaks these things down like this. Okay. So if you have in Lagrange theorem, we have the different relation, different equivalence relation. But if you use this equivalence relation, what we say is, let's say you take this A and this equivalence class, we call this as the orbit of A. Okay. We call this equivalence class as the orbit of. Okay, if you take X, then the equivalence class is the orbit of X. So this equivalence class is basically the orbit of A under the H. Okay, and so why we care about orbit? There is a beautiful theorem that will come later. I'm not sure if we are going to do it. There is a, if you're interested, I will just give you a heads up. There is a beautiful theorem. It's called the orbit stabilizer theorem. So this theorem will going to come. I'm not sure if you do in the course. If you don't do in the course, probably I would say this is one of the very interesting theorem. You can actually check it out if you are not doing the course. Okay, so this is a very good theorem. It will come later, but for that I'm just defining this. This kind of things we will directly use at the time, but we'll just do it. So in that sense, we care about orbits. Okay, since I mentioned this theorem, let me also say what is let's do what is the stabilizer also. Okay. So suppose if G is a group and it acts on the set A, the equivalence classes, these are all G acts on A. So this is called the orbit of G containing A. Okay. So basically you can see it like this. You take the A and hit with all the G that is possible. Okay. And what comes is the orbit. And take all the G. So okay, let's go here. The same example you take. Let's say you take 0. Okay. And the group is Z, right? Now you take this 0 and hit with every element of this group. Okay. So if you hit with 1, it goes here. If you hit with 2, it goes here. If you hit with -1, let's say it goes Sorry, what have I write here? Sorry, it has to be -1, -2, -3. Okay, I kind of went like 5, 6, 7. Okay, that's very stupid. But anyway, if you hit with the -1, it goes here. Okay, so basically what you do is you take this 0 or take any a and look for all these elements, all the basically orbit is basically all the possibility. If you take a and hit with the element of g, it moves to different element of a, right? So basically what we are doing is you take this element and look for all the possible places, all the possible elements that this a can go if you hit by g. Collect all those things, and that is called the orbit. Okay, so if you want a little bit, this is not mathematical thing, but I don't want to say like this. But anyway, if you see, let's say you have a solar system, okay, and you take this sun here. Okay, what is the orbit of Earth? Orbit of Earth means you have the Earth here. Orbit of Earth is basically all the possible points where the Earth can rotate, right? This is the orbit of Earth. Let's say this is the orbit of Earth. Earth cannot go here. It will only rotate in this particular point, set of points. And all this set of points, if you collect, that is called the orbit of Earth. Similarly, what you do is you take an object element here and look for all the possible thing where it can goes. And, those points are called the orbit. So the names are comes in that sense. So whatever you name it, there is some intuition behind the names. But anyway, so this action is called a transitive action if there is only one orbit. Okay. So in this case, let's say we again go. I'm sorry for scrolling it again and again. But here, if you go, you take this 0, okay, and look for the possible orbits. See, the 0 will go to any n, right? Take any n, and if you hit with the n times n dot 0, this is nothing but n plus 0, and that is equal to n. Okay, so this 0 will goes to every n. So if you look at the orbit of 0, this is basically Z. Okay. If such a problem happen, but here you can see that will not be the case for the second one, but anyway. So in the special case when this there is only one orbit, such actions are called transitive actions. So let's do what is a stabilizer. So if you take a element A here, the stabilizer of A in G is basically the set of all elements in G that fixes A. So here you have some element A here, and then you are hit this A by this G, right? Now what happens is sometimes this G will not do anything to the A. Okay. And those are called collect all the G which does nothing to A. And those are called the stabilizer of A in G. So it is called stabilizer because it's kind of stabilize your A. So under this action, these elements stabilize your A. It does not do anything to the A. Okay. So that is what it says. Okay. So this is a stabilizer of one element. Now there is another property which is called the kernel of the action. So the kernel of action is the set of all elements of G that acts trivially on every element of A. Okay. So this is a set of all G in G. Maybe I'll just leave it for a few seconds for you to recall. So set of all G in G such that G times A is A. So basically it does not do anything to any element. Okay. In this one, these are set of all G which does not do to this particular A. Kernel is basically set of all G which does not do anything for any A. Okay. So maybe take maybe 30 seconds or something, try to read it and try to understand it. It might take a while to understand it. Okay. Maybe I'll move to the kernel now. See, this is actually one problem with this online course and writing in the board. If you write in the board one can move on to the next one, but the people can still have the view of the the previous one. But when you teach in this online, this is not possible. Okay, so I understand. I hope you can understand little bit, but let's do some example to see it. Okay, so this question basically says prove that the kernel and stabilizer are subgroups, but we will come back to later. But let's compute some kernel and stabilizer so that you will get the idea of how it looks like. So here the question is find the kernel and the stabilizer of the action of G on itself by conjugation. So basically you have the G and it acts on itself by how do you take? You take a G and G dot H is nothing but G H G inverse. Okay. So this see this as a set. Okay, not a, this see it as a set, and this H belongs to this set, and G is basically the group element of G, and this acting on this by the conjugation. Okay. So our aim is to find the kernel and the stabilizer. Anyway, I will write what is the kernel here. Kernel definition is a set of all G in G such that G dot A equal to A for all A in A. Okay. So in this case, what happens is G acts on A. Okay. So this is a set, this is a group. So let's compute what is the kernel for this particular action. So this is nothing but set of all G in G. So probably I'll write a kernel of conjugation. Such that G dot H is equal to H for all H in G, right? So what is the G dot H? So set of all G in G such that G H G inverse equal to H for all H in H. Sorry, for all H in G. But this is nothing but set up. I'll just write all these things here. But what you do is take this and multiply by G on both sides. Okay, so this kind of gets cancelled. So GH equal to HG. So what is this element? What is this set? I mean, you can open your mic and speak. See, it would be nice if there's some interaction. Otherwise, I'll just, it's like I was the only one who is talking. But here you can see this kernel is, you already know this set. So this set is nothing but, somebody is saying something. Okay, this set is basically the center of G. Okay. So how the center of G is defined? If you don't remember it, go and recall this one of the very important subset of a G. Okay, so if you have a group, the center, this commutators, these are very important subset. Maybe commutators you may not study in this course itself. I guess we will not do that. But this is also very important subset, but may not be very easy to say it, so we will not maybe may not study. But the center is one of the very important subset, and we'll study in this course also. Okay, so the kernel is basically the center. Okay, so let's this kernel we have computed. Let's look at the stabilizer. Okay, so let A belongs to G or H belongs to, maybe A belongs to J, right? Sorry for changing the notation in between. So GA, which is so this is the symbol. I think I haven't mentioned it here. Yeah, the stabilizer of A is basically denoted by GA. Okay, and again recall it. This is a set of all G in G. which kind of does nothing to A. Okay. So these are set of G in G, such as GA equal to A. Okay, so what is a GA in this case? Set of all G in G such that G dot A is what? GA G inverse. This is equal to A. Similarly, multiply on the both side by G. So what is this group? This subgroup also we have studied it. Okay. So this is basically the centralizer of G, centralizer of A in G. Okay, so this is centralizer. Okay. So this is center. So all the subgroups, center, the centralizer, etc., they kind of comes as a kernel and stabilizer of this particular action. Okay, and this is again one of the action. There can be many action you can define, and all this kernel and the stabilizer they give rise to different subgroups. Okay, here if you see this is G acts on itself by conjugation, right? But here also you can change a different action. There's a left action, etc. there. But also you can change this set also. So the reason that group action is important is one of the reason is basically here you can put some set here, and whatever comes is a subgroup. Okay, so in that sense, if we use the kernel and stabilizer, we can come up with the different subgroups also by changing this particular set. Okay, so what we observe here is here you get center and here you get centralizer. So basically these are all subgroups. So let's go on to prove that this kernel and the stabilizer is actually a subgroup. Okay, so this is the next exercise. So again, what is the kernel? Kernel is basically the set of all G in G such that G dot A equal to A for all A in E. So in order to prove something is a subgroup, what we do is we just need to prove three of this. One is the identity belongs to, let me call this kernel as K. Okay, identity belongs to K. So to show K is a subgroup of G. So it is enough to say the first one identity belongs to K. What is the second one? A comma B belongs to K. We want to prove that AB belongs to K. Okay, so this is another one. And what is the third one? You want to say A belongs to K, then A inverse belongs to K. So these are the only thing that we want to prove. Okay, so let's prove one by one. Let's say Y1. Okay, what happens with, see, just recall this one. Okay, try to remember this. Maybe first time when you read it, it may be a little bit hard to remember, but probably try to remember it. The kernel is set of all elements in G such that G times A is A. So Y1 belongs to K because what happens with 1 times A? 1 times A is A, right? So thus 1 belongs to K. So again you can see here why this property is needed. So this property in that group action, it's randomly, if you see it randomly was put there. It was put there in such a way that these things became a subgroup. So these are all important subgroups, and you want these things to be a subgroup. So it was defined in such a way these things became subgroup, etc. So maybe I will not repeat it again, but you kind of understand why that was defined here. Okay, so let's take two elements in K. We want to prove that the product is in the K. So let's take A comma B belongs to K. Now I want to say A B belongs to K, right? So what does A comma A belongs to K means? So A times G equal to G for all. Uh, okay, I think maybe I should. Okay, we'll change the symbol here. I call this as G and H. So sorry to change in between. So the reason is, we are acting on the group here, on the group A, and I don't want to use the symbol A and B to denote element of the group G. So rather, this was very confusing otherwise. So I rather start with the, let's say G1 or G comma H I will use. Okay. So this K, you see, it is a subgroup of G. Okay. So it's a at least now it is a subset of G. Okay. So this you will recall it. So what happens? What is the G belongs to K means? So G dot A equal to A for all A belongs to A. Okay. And H belongs to K. This implies H dot A equal to A for all A belongs to A. Okay. So what we have to do here, I want to say that this GH belongs to K. Okay. So let's start with GH and then act it on any A. Okay. So let's start with any A belongs to A and consider GH dot A. Okay. So this is nothing but G dot H dot A. But you see, H is the element of K, right? So H dot A is nothing but A. So this is G dot A. But again, G is the element of K, so G dot A is A. So this is nothing but A. So what happens is GH dot A is A, and this is hold for every A. So that means GH. So this implies so GH belongs to K. Okay. So this we have proved also. Now the last one is if G belongs to K, I want to say G inverse also belongs to K. So let's start with G belongs to K. What does it mean? It means G dot A equal to A for all A belongs to K. Sorry, A belongs to A. I want to say what is the G inverse dot A. This is my claim, right? My claim is G inverse dot A is actually A. But we know nothing about G inverse dot A. Okay. So from here, how do you proceed is the question that you can ask. Okay. So, but what we do is we start with this one. So let's prove this. G inverse dot A equal to A for all A in A. So this is what you want to prove. So let's start with the A in A. So what we know is we know that G dot A equal to A, right? This we know. Now what you do is you multiply both sides. So take this element and do G inverse on both sides. Okay. Now what happens? Here you use the property of the group Xn. This became G inverse G times A. This is G inverse dot A. What is this one? This is a 1 dot A, which is A. Okay. So you have proved that G inverse dot A is A. So all the three properties are satisfied. So thus this is a subgroup. Okay, so let me look at the time here. And I just want to just give me 1 minute. I want to see how many problems I have. Okay, there's not much I have. So yeah, there's two here and maybe yeah, and I have a few more in the book. So okay, so we have time. So let's do the next one. So let's prove that stabilizer is also a subgroup. Okay, second one. What is GA? This is a set of all G in G, such that GA equal to A. So in this case, you see that G is fixed here. Sorry, A is fixed here. So let's try to prove it. So the first again the same three properties that we want to prove. So I think you might know what are these three property. Identity has to be there, and the product has to be there, inverse has to be there. Okay, so let's do it here. Why? Okay, what is 1 dot A? 1 dot A is basically A. It's a property of group action. Okay, thus okay. So let's say let G comma H belongs to G. Okay. So basically G comma H belongs to G means what? G dot A is A and also H dot A is also A. So now let's look at GH dot A. GH dot A is nothing but G dot H dot A. It's nothing but G dot A. Because H A is nothing but A. And this is again A. Okay. So the second property is also satisfied. So thus GH belongs to G. So anyway, these are all very easy. The same thing we want to prove. Let again G belongs to GA. So we want to say G inverse belongs to GA. So what does it mean by G belongs to GA? G dot A is equal to A. That's what it says, right? This implies suppose I multiply both sides by G inverse dot G dot A. This is nothing but G inverse dot A. Okay. So what is G inverse dot G dot A? This is G inverse G dot A. It's nothing but G inverse dot A. What is this? This will be 1 dot A, right? So we are done here again. So basically we have proved that G inverse also belongs to GA. Okay, so this is the easy part. So what we have seen here is we have okay, now let's go on to draw something here. See, I have a G A and A here. Okay, so there are three things we have seen here. One is orbit, another is stabilizer, another is a kernel. Okay, so this kernel and stabilizer are basically subgroup of G. Okay, and orbit is a subset of A. Orbit need not to be a subgroup. Orbit is a subset. Okay, so since we have done these things, I will just state what is the orbit stabilizer theorem. But we are not going to prove it here. Probably we will do it in the class. So what orbit stabilizer theorem says is the following. So there is a bijection between G by stabilizer of A or G by GA. I will call G by GA. GA is the stabilizer of A to orbit of A. Okay. So this is the orbit stabilizer theorem says. Okay, so this is okay. So the proof we are not going to do here. Proof is not hard. From I mean, maybe not very easy also, but from here you can easily prove it. It's as short as the Lagrange theorem. If you look at the Lagrange theorem, the proof is short, right? This is kind of the same. And in this case, if you change this action uh, to the left multiplication, so we have done. I think in the class we have done what is the left multiplication, right? So you take this. G here, you take the G, okay, and you take the set of all cosets GH, okay, where H is a subgroup of G. Okay, now what happens is this G will act on this set GH. How it acts? If you take a G times, let's say, let me write maybe, let's say some element H will not H actually. Let's say G1 dot GH. This is nothing but G1 G dot H. Sorry, G1 GH. Okay. So define action like this. And then if you look at the orbit stabilizer theorem, this is with this particular action, if you look at orbit stabilizer theorem, what you get is basically Lagrange theorem. Okay. So in that sense, you can actually directly see why orbit stabilizer theorem is, kind of a big theorem, because Lagrange theorem, which is very useful if you remember, is just a corollary of orbit stabilizer theorem for particular action here. Okay, so if you change a different action, and here also the set is particular set and particular action, it's a consequence of it, it's a orbit stabilizer theorem. But you can here change the orbit, sir, you can change the set here, you can change the action here. So now you can see how interesting this orbit stabilizer theorem is, right? So yeah, basically I thought I will do this Lagrange theorem as a consequence of orbit stabilizer theorem, but anyway, we'll leave this part. But the orbit stabilizer theorem basically says there is a bijection between G based stabilizer. This is a this is a subgroup. Need not be an. I'm not sure if I think the stabilizer need not to be a normal subgroup. Just give me a minute. Yeah, I think stabilizer is a normal subgroup. Let's try to prove it also. Okay. So this is a quotient group. There's a bijection between these two things. So that is what the orbit stabilizer theorem says. But let's forget this for a minute. Orbit is anyway done in the class. I think the stabilizer and kernel we have it here. Okay, so since we have said this, let's prove this. So let's ask the question here. So is stabilizer of a normal subgroup? So what does that means? Let's say G belongs to the stabilizer. Okay. So what we are claiming is whether H inverse also belongs to stabilizer for all H in G. So this is what we want to see. Well, in general, it will not be, I think. Let's try it here, but I don't think it will be. So if you take H inverse times A, it will not be, So this is not, in general, this will not be a normal subgroup, but you can try to think of a counterexample. I currently don't have a counterexample, but I can check actually. See, basically, if you want a counterexample, see, you have seen here, right? Under conjugation, the stabilizer is basically the centralizer, right? So you can directly look at some group and take an element and look at the centralizer and then try to prove this centralizer is not a normal subgroup. Okay? Something like that you can do. But if you look at the kernel, and the answer is yes. Okay. And in fact, there is a relation between the kernel and the stabilizer. But I'm not sure if I want to say all these things. This is the first course, but there is a relation. If you want, I'll just write it down. So kernel here, let me call the kernel as K. This is nothing but intersection A in A, G A. Okay. So basically, what is GA means? GA kinda fixes A, right? So let's go here. So this GA is whatever the element that fixes this particular A. So kernel is something that fixes every A. Okay. So if an element belongs to the kernel, that means it fixes every A, right? So any element of kernel is an element of GA for any A, this is an element of GA. And you can prove the converse also. It's very easy to prove. So once you prove that, what you get is there is a relation between where I write it here. Keep it as exercise is very easy to prove. Okay. Okay. Anyway, these are the few small things that we did. So let's go to the next one here. Okay. So this is two more problems. So let's try to solve this. So the first problem says that let G be a group and A take the set A also as G. Okay. Suppose if G is non-abelian, then the map defined by G dot A is AG. Okay. So basically this is a left multiplication. You are multiplying by the left. So not left but right multiplication. You are multiplying by the right. Okay. This does not satisfy the axioms of group. Okay. It does not satisfy the axioms of the left group action. Okay. See here what I mean is there is a sometimes people call the left group action, right group action, etc. Left group action means you are doing it in this way. Right group action is you are doing it in the other way. So the problem comes is basically G dot A, writing it AG. If you write it as GA, there will not be any problem. But anyway, we will see how it goes here. So what we are going to we are trying to say is this action does not satisfy the axioms of the group action. Okay. So if you observe, the first axiom is anyway satisfied. If we look at 1 dot A, this is nothing but we are doing this problem. Okay, this is nothing but A1, right? But that is A. So the first the this kind of normalization, this is the second property of group action. This is anyway satisfied. Okay, let's look at the first property. What is the first property? It says that G dot, let's say something like that. G dot H dot A is nothing but GH dot A. Okay, so this is the first property. This has to be true for all G, H belongs to G and A belongs to A. Okay. So let's try to compute it. So what is the G times H times A? Sorry, G here I am not writing it. Okay. Okay, so what is this? This is nothing but A H G. Okay, so you can see it here. So what is GH dot A? This is nothing but A GH. Okay. So let's now once you observe it, let's try to formally prove that. See here you can see that forget these two elements. These are same element, right? But HG is never need not equal to GH. Okay, so that is what we are going to prove. Okay, so this is not equal because you are working with a non-abelian group. In general, these are not equal. So this property will not be satisfied. But let's write it formally. So here we start with the G is a non-abelian group. So let me write how to write formally. Since G is non-abelian, so there exists G comma H in G such that GH is not equal to H. Okay. See, in general, if you look here, some of them can be equal, right? Some G and H can be equal, some cannot be equal. Since it is a non-abelian group, means there is at least one GH that they are not equal. So we choose such a G and H, and then we proceed. Okay. So what happens with G H G dot H dot 1? Let's say this is nothing but H G. Okay. So here you observe here. I take A as 1 here, so this is HG. So GH dot 1, this will be nothing but GH. Okay, and they are not equal. So that means since this is a statement needs to be true for every G, H, and A, So I have come up with a G, I have come up with a H and A, for which this is not true. So that means this property is not correct. So let's do the second one. So what it says is, if you do in this way, it is not a group action. But if you kind of do it in the with the inverse, then it is a group action. So let's do that one. So what is this? So G dot A, this is nothing but A G inverse. Okay, and here the G can be anything. It can be abelian, non-abelian, doesn't matter. And we claim that this is a group action. Okay, so this is anyway easy. 1 dot A is nothing but A1 inverse. This is A. 1 inverse is just identity inverse identity. Okay, so G dot H dot A. What is this? This is nothing but G dot A H inverse. So here you have to kind of do this, and that is nothing but A H inverse G inverse. Right. Now let's look at the other one. GH dot A. Let's look at this one. This will be nothing but A GH inverse. But GH inverse is nothing but H inverse G inverse. So these two are equal. Okay. So that tells you that this is a group action, but the other one is not a group action. Okay, so let's maybe, okay, I will just add one more question. So far what we have done is we have defined what is a group action, but the thing is we can see the group action a little bit differently. So I think this might have been done, but let me say it here. So suppose this is a group action, right? A group action is basically a map from G cross A to A, right? Such that it satisfied two property. 1 dot A is A, and G dot H dot A is equal to GH dot A. And this is for all A in A, and this is for all G comma H in G and A. Okay. So if anything that's at any map that satisfies these two is a group action. Okay. But what we can do here is you can see this is a map from two coordinates, right? So let me fix a G here. Okay. And then see what happens. So if you fix a G, then what happens is this kind of induces a map from A to A. What it does, it takes A to G dot A. Okay. And this probably I called it as a sigma G. Okay. So this sigma G is actually a permutation. Or what I mean is it's a bijection. So basically, if A is A is a finite set, then this sigma G belongs to this S of A. Okay. So this is basically bijection. And if you take this map from G to S of A, you take this G. What I mean by S of A is a set of all bijections. See, if you observe here, this is basically symmetric group. Okay, this is a symmetric group. On instead of the symbols 1, 2, 3 to n, you are just calling it as A1, A2, okay, till AN. Okay, so whatever you do here, this is basically a symmetric group. S of A is a symmetric group. Okay, so here is a group structure is here. Okay, this A, G goes to sigma of G. This will be a homomorphism. Okay. So these two things are kind of equivalent. So saying that G acts on A is the same as telling that giving a homomorphism. Let me call this as CF. Okay. So it's same as giving a homomorphism from G to the symmetric group of A. Okay. So I haven't proved these two things, like why these are equivalent, I haven't proved it. Why this is a bijection, I haven't proved it. And also why this is a homomorphism, I haven't proved it. But let's just assume it for now, and maybe we'll just prove the homomorphism part and leave this bijection part. You can see it is a bijection because see it is a bijection because you can always do something like this, and you can try to observe here. Okay, so whatever the element comes, you want to prove subjective and injective, right? You can easily prove it. Try to probably prove it. Okay, so let's maybe just prove that this is a homomorphism. So homomorphism means what I want to prove. I want to prove f of gh is nothing but f of g, f of h, right? So what is f of gh? It's a sigma of gh. We want to prove that is equal to sigma g, sigma h. Okay. So what is the sigma g and the sigma? These things, all these three are the elements of SA, right? So they are all mapped from A to A, all of this. So in this case, the product is, it's a composition. Okay. So that means what you want to prove is you take a sigma gh and basically apply A onto that, and you have to say it is equal to, if you apply A to this one. Okay, you want to say applying A is basically the same. So what is this? What is the sigma gh of A? Let's go here and see. This is a, this one I can multiply. I just have to put it in the front. Okay. So this is gh dot A. Okay. But this is nothing but g dot h dot A. What is h dot A? H dot A is a sigma h of A. Okay, g dot this. This is nothing but sigma g of sigma h of A. Okay, so here you can see that this is a, so this kind of tells you this is a homomorphism. So we have homomorphism from G to symmetric group of A. Okay. And given any homomorphism from G to symmetric group of A, you can also prove this statement. So these are kind of equivalent statements. So now what we prove is we will prove exercise here. So maybe we'll prove one question here. Maybe. Okay, maybe I'll just read it out what it says. So what we are going to prove is we have studied what is the kernel of a group action, right? So this kernel of a action of the group G on the set A, this is basically same as the kernel of the corresponding this representation. So this map, this homomorphism, which comes from here. Okay, see, here I have proved it's a homomorphism. I just skipped the fact that it's a bijection. Okay, so this map is a bijection, you can easily verify. Okay, so what it says is there is a kernel here, right? Because it's a homomorphism, we can talk about the kernel. And for the action also, we have said something is a kernel. Okay, now the question is what is the relation between these two things? Okay, and the problem says this the kernel of the action of group is same as the kernel of this particular permutation representation. So this is the homomorphism. This kernel is basically same as the kernel of the group. It's the kernel of the action. Okay, so let's try to prove it here. And maybe if there is a little bit more time, then probably I will introduce what is a dihedral group. Uh, I'm not sure if we have done it. So far I have checked it till week 6, I think. It's not that the dihedral group is not till week 6. I'm not sure if it is done in the week 7. But if there is a little bit more time, then probably I will introduce dihedral group. Okay, so this both kernel are same is what we are going to prove. Okay, so what is the first kernel? Kernel K. This is a set of all, this is a set of all G in G such that G dot A equal to A for all A in A. Okay, so this is how we define the kernel. Now we have another thing, G to SA we have map, and let's say call it as a kernel, let's say F. And we have a kernel F here. Okay, so the question says this kernel F is equal to this kernel, whatever the kernel we got, that is. So basically what it says is kernel F is set of all G in G such that G dot A equal to A. Okay, so let's try to prove it. What you do is if you have two sets, you want to say it's equal, we prove containment, right? So let's prove it here. So let's prove the first containment. So this one, let's prove it. Okay. So let's start with the G belongs to kernel of F. Okay. Not G. Yeah, G belongs to kernel of F. That means what? Sigma G is 1. Or sigma G is basically identity map. Okay, what does that tells you? Sigma G, it's a map from A to A, right? What happens is, this is the identity map is what it says. What is the sigma G of A? Sigma G of A is G dot A, but this belongs to kernel, that means this is equal to identity. What identity map does is it's map A into A, right? So that means G dot A, this must be equal to A. Okay, so this must be equal to A. Okay, so what does it tells you? And this has to be anyway happen for all A because identity does this for all A. This is sigma G belongs to your kernel. Sorry, not sigma G belongs to kernel. This tells you just look at only this part. You look the other part you forget. Just this part if you look. This tells you that G belongs to uh, this kernel. Okay. So this tells you that G belongs to this kernel. Okay, let's prove the other way around. Let's prove that this belongs to this. Okay. So basically what we have is, let's start with the G belongs to this part we are going to prove. So let's start with the G belongs to this set. It's a set of all G in G such that G equal to A for all A belongs to A. Okay. And we claim that G belongs to kernel of F. So what is F? F is a map from G to SA, mapping G to GA. So G to sigma G. Okay. So what is the sigma G? Sigma G is a map from A to A. It maps A to, okay, probably I'll write it down properly here. So F is a map from G to SA. It maps your G to sigma of G. And sigma G is actually a map from A to A. It maps A to G dot A. Okay. So now here your kernel. Okay, this is the claim, right? Yeah, this is the claim. I want to say this. This is my claim. Okay. So that means what? I want to say sigma of G belongs to kernel F. That means I want to say the sigma of G is identity. That is what I want to say. So basically what I want to say is sigma of G is identity. Okay, so basically what does that mean? It means sigma G of A is equal to A. This is the claim that we want to prove. Well, that is obvious. What is the sigma G of A? Sigma of G of A is nothing but G dot A. But since G is in this set, this GA is equal to A. So we are done. Okay. So what we have proved is the following. Let me go back here. So we have a group action here. On this group action, what you do is you fix a G here. Okay. If you fix a G, this will give us a bijection from A to A. Okay. Maybe I will prove it is a bijection also, just for the sake of completeness. It might already done it, but I just want, we can do it for sake of completeness. Okay. So you got this sigma G, this is a bijection. Okay. So that means by changing different G, you get a different bijection. Okay. And hence you will get a map G to SA, where SA is a set of all bijection from A to A. Okay. So this is a symmetry group, of course. Instead of n letters, we are having n symbols, different symbols. It's all the same. Up to isomorphism, they are all the same. Okay. So what you do is you take this G and you get it to sigma G. Okay. And one can prove this is the homomorphism. The homomorphism, you have to use this property. And again, suppose if you give a homomorphism like this homomorphism induces a group action. Okay. So how do you, from this homomorphism, given this homomorphism, how do you give a group action? What you do is G dot A, you define it as sigma G of A. Okay, so you can define like this. So these two things are, in some sense equivalents. Probably I will keep like this here. So these two things, these are equivalent definitions. Either way, you can define a group action. Okay. So since this is the homomorphism. If you have homomorphism, you also have a kernel, right? So there is a kernel for this homomorphism. And what we have proved is that kernel is basically can be written. Where is this? Yeah. So that kernel, what we proved is you have this map, and the kernel is basically this particular map. Okay. So if you take conjugation, etc., this kernel became the center itself. Okay. This we have. Maybe I'll just quickly prove that it's a bijection, and maybe we'll stop. And I'm just thinking if there is any good, So probably I will just define this dihedral group alone. Maybe I will take 5 minutes, define the dihedral group. Because the dihedral group, why I want to define is it kind of comes from the group action. So once you have dihedral group, we can talk about a lot of group actions. So okay, so I want let's just prove this a bijection. Okay, this I have proved it. So let's prove. So for bijection, what we need to prove? You want to prove the injectivity and surjectivity, right? So how do you prove the injectivity? Let's say you have G dot A1. Suppose this is equal to G dot A2. Okay, maybe this is not how we have to do it. We did sigma G of A1. Suppose this is equal to sigma G of A2. Okay, so we were proving the injectivity. We want to prove that A1 is equal to A2. Okay, so what we want to do is this implies A1 is equal to A2. Okay, let's write it down. What is this? G dot A1 is equal to G dot A2. Okay, now I want to say A1 is equal to A2. What do we do? That's the obvious way. Multiply by the G inverse. Okay, G inverse dot G dot A1 is nothing but G inverse dot G dot A2. And you can group these two things together. So this is the property here. Use this property, group together. This will cancel out. Then we will have 1 dot A and 1 dot A2. Well, that is A1, A2. Okay, so this is A1 equal to A2. So this proves injectivity. Okay. So let me prove subjectivity also. Maybe where can I prove? Probably here I will prove subjectivity. So just recall this map. The map from A to A, taking A to G. Right. So we want to prove it is subjective. Okay. So let's start with A belongs to A. Okay. We want to say that we claim there exists B in A such that sigma G of B equal to A. Okay. So how do you do that? You take this B to be G inverse dot A. Okay. Then now apply sigma G of B. This is nothing but G dot G inverse dot A. Well, this is nothing but A. Okay. So that tells you it is a surjection. So we got some B maps to A. Okay. So this is, I'll just write a surjection. Okay. So we proved this also. So the moral of what I was actually trying to say is there is two definitions here, and these two definitions are equivalent. See, when you first time do that, this may looks a little bit hard. These two things, but take some time. It will eventually become easy. So I remember that the first time I do that, uh, maybe 1 or 2 days, maybe at least one day, I couldn't able to see how these things are happening. But basically, what you have to do is you just fix a G, you will get this sigma G. And if you look at the sigma G, it's an element here. So you can give this map. And again, the other way around also you can give. But it looks hard. Okay, so there is a two definition. And the kernel here and the kernel here are the same. Okay, so that is what we have proved. So let me just do this dihedral group and then we will stop. So why I want to do the dihedral group is this kind of dihedral group. These are good examples of group actions. I mean, not group action, but you can see these groups acting on some set easily. So that's why I just want to do that. Okay. So what you do is let's play a little bit of little game. Okay. So let's take a square from here. Maybe I'll maybe draw a square here. A square. Okay. And so basically I have a sheet of paper and I cut a square from here. Okay. But I'm just going to map this edges. Some color I gave to this edges. Okay. So maybe I will give some color here. Different color I give, let's say. Okay, so now you gave some color. Now what I have to do is, what are the operations that I can do here such that, so basically you take this, you cut it out, now you take it in your hand. Okay, now what are the different way you can put this thing back here? Okay, so that was the question. Okay, for example, one way is that I'll just copy it again here. We have pasted somewhere. Okay, so this is the image that we start with, whichever it is here. Okay. So now what I can do is I can I can rotate it to the 90-degree, right? So this image, if I rotate it to 90-degree, okay, what you get is basically the same image you will get, but now the colors are different. Okay, okay, this is one thing I really don't want to do is change the color. Okay, let me just quickly pull up the color. Okay, so if you observe that, let's just look here. Okay, if you observe that these two are not the same square. I mean, you take the square, rotate it, and you put it here. But if you observe that since I map a different colors here, this is kind of different now, right? So instead of color, let me just draw it with some letters. So here I have a square here. Let me call it A B C D, and if you rotate by 90-degree, you will get A B C D. Okay, and these are different squares. So I can do 90-degree here, and I can put here. I can also put 180-degree. Okay, and that also I can able to place it in the same. So basically what you're doing is you cut it, and then you cut this piece out and you take it out. Okay, now what are the different ways you can put it back inside? Okay, I can rotate it and put, I can rotate it to 180-degree and I can put it, I can rotate it in 270-degree also. Okay, so maybe I will just write it here. So I can rotate 90-degree counterclockwise. I can rotate 180-degree. I can rotate 270-degree. And if you rotate 360-degree, that is actually same as identity. Okay, and similarly you can check going this way. So I'm going in the counterclockwise, right? If you go in the clockwise 90-degree, that is same as counterclockwise 270-degree. Okay, you can check that. So keep it as an exercise. Okay, it's a fun exercise. Cut a piece of paper, uh, put 4 colors here, or maybe just map A B C D, and then do all the possible thing that you can do. Okay, what you can, another thing you can do is you can flip around this axis. Okay, so let's say if you have A B C D here, and you flip it around this axis, what you have is the following. You have a DC AB. Okay, and you can flip around this axis, right? You can flip around this axis. You can flip around this axis. Okay, so that gives you 4 flip. Okay, so I will call this as maybe flip 1, flip 2, flip 3, flip 4. Okay. And if you take all these possible operations, what you can see is this is basically forms a group. Okay, and this group is called a dihedral group, and the people call this as 2 times 4. Okay, basically they write as D2n, but n depends on the size of this polygon. Here there is a 4 sides, so I am calling it as 2 times 4. If you have a n gon, let's say 5 gon, you have something like this, then you will get 10 elements in the dihedral group. Okay, depending on the n, depending on the n gon, you will get 2n elements, and this kind of group are called a dihedral group. So basically, what happens is there is a flip here. Okay, so if you have a n gon, let's say I will draw a 5 here, maybe. How many? It's 5, right? Yeah. If you have 5 gone, what happens is there are, how many flips you have? Like this. Okay. From this vertices to the opposite side. Not. So every vertices connected to the opposite side, you have one flip. Okay. So you have 5 flip. And you have rotation also, 5 different rotation you have. So basically you will get a 10 operation here. So any n gun you get, there is a n rotation and there is a n flip. Okay. So that is basically 2 n elements will come. And you can prove that anything else is also one of these two. Okay. You can prove it. It's not easy to prove it. Okay. But you can prove it. So the reason I'm skipping here is one actually has to prove. See, basically there can be many operations, right? For example, if you just look at this 4, you can see this element. Let's say here you have ABCD, right? So you can see this as a permutation of ABCD. So here A maps to D, B maps to A, C maps to B, and D maps to C. So this dihedral group, you can see it as a subgroup of S4. You can see it. But the question is all the permutation gives you how do you say, is all the permutation gives you element of a dihedral group. For example, let's say I have draw something like this. Okay. So I have A, B, C, D, but now I can permute this A and D alone. Okay. So D here and A here, B, C, that remains the same. Now the question is this is also an element of dihedral group, and this is not the element of dihedral group. Okay, because you can see, because you're taking the square out and you're trying to put it inside. You cannot put it this way. You draw a piece of paper and you can do, unless you kind of how do you say, one direction you go, another direction you go, and it will just kind of break, and it's not possible to put it back. You try to put it back, probably take a piece of square and try to put it back. So not every element of a symmetry group is an element of dihedral group, but some elements are, and these are the only elements. There are n rotations and n flips, but one has to prove that these are the only possibilities, and we can prove it. It's not hard. So the main idea in the proof is basically, see, if you take a edge here, A and B. So the main idea is this A and B has to be still adjacent, and the adjacency are preserved, right? Under the dihedral group, the adjacency are preserved. But if you look here, uh, here this D and C are adjacent, but if you look here, they're not adjacent. So you need to use that, and you have to prove this a dihedral group. Okay, the reason I am telling is this dihedral group will act on the square. So how the dihedral group act on the square? If you take a 90-degree, it kind of rotates to 90-degree. That's all. Take the square, this 90-degree act on the square by just rotating. Okay. Maybe just give me a minute. It does not act on the square, it acts on the set of all configuration of the square. So basically you have this square, right? I have mapped see, where is this here? So so basically you take a square and then you are going to put it back in, and there are many ways you can do it. These are called when you put it back, these are called symmetries, and this dihedral group kind of acts on the symmetries. Basically these are all the symmetries. Okay, maybe we'll stop here, but this groups are, the reason I'm defining is this is one of the interesting example, and you can kind of see it geometrically, and you can also see this acts on let's say Rn, etc. You can make it act. Okay. Anyway, we'll stop now. We'll meet next time maybe.